Welcome back to Control System Lectures. In this video I'm going to discuss the Routh-Hurwitz criterion and the Routh array. Now before we just jump right in, I want to give you a little bit of background knowledge so that you understand why this method was developed and how it's used in classical control theory. Now if you've been following along with my videos or already have a basic understanding of classical control, then you should know at least two things right now. The first is that in order for a system to be stable, all of the roots of the characteristic polynomial need to lie in the left half plane. And since the characteristic equation is the denominator of the transfer function, then the roots of the characteristic equation are the exact same as the poles of the transfer function. And these roots all must lie to the left of this vertical imaginary line, or all negative real components, in order to have a stable system. I'll briefly explain why that is right now by looking at a transfer function with a single pole, 1 over s plus a, where a is a variable and it can either be positive or negative. And in this case, the root of the characteristic equation is s equals negative a. So when a is positive, s is negative, and when a is negative, s is positive. Now we can take the inverse Laplace transform of this transfer function to get the time domain representation. And this is e raised to the root times t, and you can either write the root as negative a or s, whichever you prefer. Let's take the case where a is positive, and since s is negative, this root exists in the left half plane. And if you plot this in the time domain, you'll see that the signal will tend towards 0 as time approaches infinity. And this is stable since any signal into this transfer function will ultimately die out and the system will be at rest again. However, if a is negative, or the root is positive, then the response will blow up into infinity, which is obviously unstable. Now we can stack any number of these poles up to produce a transfer function of higher order. I'll write a transfer function here consisting of 3 separate poles, 2 in the left half plane and 1 in the right half plane. But we can always simplify a transfer function written like this using partial fraction expansion, which in this case turns multiplication into a summation of 3 separate single-poled transfer functions, all with different constant gains. And when we take the inverse Laplace of each of these, we see that the response is the summation of a bunch of different exponentials. And no matter how stable most of them are, all it takes is one to blow up to infinity to make the whole transfer function unstable. And this is why even if a single root is in the right half plane, your entire system is unstable. So we know that we can determine the stability of a system by solving for the roots of the characteristic equation. But the second thing that we know is that calculating the roots of a system for anything larger than a second-order polynomial becomes time-consuming and possibly even impossible in closed form, as would be the case if you were given this fifth-order polynomial and asked to solve for the roots. So your question might be, how can I determine stability of a higher order polynomial without solving for the roots directly? And one of the ways that you can do this is by using the Routh-Hurwitz criterion and the Routh array. Now going through the proof of the Routh-Hurwitz criterion is beyond the scope of this video, but I will cover it in a future lecture if there is enough interest in seeing it. The Routh-Hurwitz criterion states that all roots of a polynomial lie in the left half plane if and only if a certain set of algebraic combinations of its coefficients have the same sign. And this statement, a certain set of algebraic combinations, is really just a cryptic way of saying that you perform the steps to fill out the Routh array. The great thing about the Routh array is that you don't have to actually solve for the roots of the characteristic equation. It allows you to assess stability just by looking at the coefficients of the polynomial. Now when you're trying to assess the stability of a large order polynomial, the first thing you should notice about the coefficients is their sign. If all of the signs are not the same, then you can state instantly that the system is unstable. In this case, the coefficients are both positive and negative, so it's unstable. Now if every single sign of each coefficient is negative, then you can always multiply that transfer function by a gain of -1 just to get all positive values. Remember that in order to solve for the roots, we're setting this equation to 0, and we can always divide out that -1. Therefore, from a stability point, there is no difference between all positive and all negative values. So in general, I'll refer to all the same signs as just being all positive. Therefore, I can say that if any coefficient is negative, then the entire system is unstable. Let me explain why. If you build up a transfer function with a series of poles, then the only way to get a negative coefficient is to have at least one pole exist in the right half plane. If all you have are roots in the left half plane, then you only have positive values in the characteristic equation, and there's no way to get a negative coefficient out of that. So if you have a characteristic equation with at least one negative coefficient, then you can instantly state that that system is unstable without having to go through the process of filling out the Routh array. However, you can have all positive coefficients and still have either a stable or unstable system. Let's demonstrate with this transfer function. The first part has roots at 1/2 plus or minus j times the square root of 3.75. The second has a root at -2, and the third a root at -1. This system is clearly unstable since there are two roots in the right half plane. You can see this from the positive 1/2. However, when we multiply all of these out, we get one polynomial with all positive coefficients. So this just goes to show that you can have an unstable system with all positive coefficients. And if we were given this system in this form, we could use the Routh-Hurwitz criterion to determine if the system is stable. And we would do this by filling out a Routh array. The Routh array is a table that can be populated with the coefficients of your polynomial with a few simple rules. The first step is to set up the table structure. When completing this table, I'll refer to entries in this direction as rows, and entries in this vertical direction as columns. Now the number of rows depends on the order of the polynomial. To start, you need to write the polynomial in powers of s that are descending. So in this case, you would start with s to the 4th, then s cubed, and then s squared, s, and then finally you would just end with the constant. And in the Routh array, the row labels start at the highest order, in this case s to the 4th, and count down to the 0th order, or 5 rows total. And the number of columns also depends on the order of the polynomial, and it's determined in this manner. Write the first coefficient in the first row and first column. Then write the second coefficient in the second row, first column. Proceed filling out the first two rows following this up and down pattern until you reach the end of the polynomial. So in our case, we'd start with a 1, then 2, then 3, 10, and 8. And if you've done this correctly, you'll see that you've placed every other coefficient in the top row, starting with the first coefficient, and then the alternates in the second row. Now there's a side note that I want to cover real quick. If there's no value for a particular power of s, then that coefficient is 0. And make sure you write a 0 in place for it because you need this in the table. And in this case, there's no s squared coefficient, so when you're filling out the table, you would just put a 0 in that place. And that's because s squared still exists, you just don't typically write it in if it has a coefficient of 0. Alright, at this point you've set up the table and you've populated the first two rows. Now to fill out the bottom rows, you need to perform a series of repetitive math operations. Now there are several great resources on the web explaining in mathematical terms how to go about filling out the rest of the rows, and I highly recommend you check them out. I've left some links in the description below. However, I personally like to imagine it as a pattern that I'm filling out rather than an equation. And if you'd like to get the math behind the pattern, then you can just visit one of those links. Let's say you're given a 6th order polynomial where each power of s has a different coefficient, a through g. You can set up your table from s to the 6th and go all the way down to s to the 0. And if your polynomial is written in descending powers of s, you can write the coefficients in the up-down pattern that we discussed up above. Now at this point, each entry in the table can be calculated from entries above it exactly in this manner. For this red box, it would be b times c minus a times d all over b. And if you think of this as a pattern, it traces the number 8. You start with the b, you multiply by c, you subtract a times d, and then finally you divide by b. Now you can use this pattern to move to the next column, but you stretch out that 8 and perform the exact same sequence. So for this blue box, you would start with the b, and you'd stretch the 8 out to the e minus a times f, all divided by b. Notice that the left side of the 8 is always the first column, and the right side just keeps expanding as you move right through the columns. Once you've reached the end of the columns, you can drop to the next row and perform the exact same steps. In this case, the fourth row would just be red times d minus b times blue, all divided by red. And then stretch out the 8 to get pink, and then stretch it out again to get the next one, and then just keep repeating this pattern. And once you have the entire table filled out, you can count the number of roots in the right half plane by seeing how many times the values in the first column changes sign. Remember that any 0 in the right half plane means the system is unstable, so all you need is for the value to change sign at least once and you know that the system is unstable. So let's use this pattern to fill out the Routh array from above and assess stability. We take 2, we multiply by 3, and we subtract 1 times 10 and divide by 2. You can see that 8 is minus 2. We stretch it out and get 2 times 8 minus 1 times 0 divided by 2 is 8. Of course, these last two entries are both 0. Now we drop down a row and we say minus 2 times 10 minus 2 times 8 divided by minus 2 is 18. Stretch out the 8, you get 0. Finally, we go down to the last row, we do our calculation, and we're left with 8. I find this pattern recognition, rather than memorizing a bunch of equations, simpler to fill out the Routh array. We can determine the number of roots in the right half plane by looking at this first column. I'll rewrite it here to make it a little clearer. You can see that the first 2 are positive, then negative, followed by 2 positive values. And you can see that it changes sign between 2 and negative 2, which means that there's a root in the right half plane, but then changes sign again between negative 2 and 18. So what we can deduce from this is that there are 2 roots in the right half plane out of the 4 roots in this system. And since there's at least 1 root in the right half plane, we know that this system is unstable. And this is exactly what we would have expected since we built this transfer function with 2 roots in the right half plane and 2 roots in the left half plane. So the Routh array worked for us and we never had to solve for the roots directly. In the next video, I'll go through a couple more examples and I'll also describe 2 special cases with the Routh array that require just a few extra steps. Don't forget to subscribe and I'll see you guys next week.